course, we may start the course. And I'll write the name once again. This statement. And the first lecture about this, the pronunciation of this is signal. Already. I'm amazed and surprised about how the students just insist on calling this signal for some reason. I don't know. You will never hear from me anything like that. The name of this is signal. Right? So be careful about that. Since the name is signals and systems, we have to describe first, for example, what a signal is. A signal is a function that we have all seen in calculus. It's a function of one free variable. At least one free variable. The free variable is also noted as the independent variable. What's an example function of one free variable, for example? It is f of t, for example. This f is a function of time. T is not taking time. So this is a function, and that automatically makes it a signal of our concern. If you have more than one free variable or one independent variable, for example, two variables here, that imposes the dimension of the signal. This is one-dimensional. Can you give examples to one-dimensional signals? Voltages, for example. A voltage across a capacitor or a current on a branch of a circuit that changes in time. It's a function of time. That is one-dimensional. Or the gene decomposition at the basis of genes. That is also sort of fewer dimensional. Or a speech signal. You record your voice, for example, sound signal. That sound signal is a variation of amplitude in time. That makes it a one-dimensional signal. Practically, this is the fundamental thing, the basic thing that we will focus on throughout this semester. We won't dive into multi-dimensional signals. We will go only through one-dimensional signals. Speech, voice, such things. A variation in a time. And we will notate, although it may or may not be time, the free variable will usually be notated as time. But we all know that it's only the horizontal axis that we are considering in a one-dimensional signal, and whatever that axis name is, that is the free variable. But we will call it time. It may or may not be time in physical reality. We'll just say it t. And this will be f of t. And it must be a function. What makes a function and what makes a curve a function, and what makes a curve not a function? A function is it has only one outcome in terms of the free variable. At one time instant, f of t must attain one value. It cannot have more than one value. For example, this is not a function because at a single time it has two outcomes like this or that. That's not possible. A function is something like this. It changes in time. That is one-dimensional. A two-dimensional signal, for example, could be f of t1, t2. This is two-dimensional. You may find it surprising or confusing when I say t1 and t2, because if t is time, what is time 1 and what is time 2? It makes no sense if these two variables are time variables in two dimensions. We are more comfortable with different definitions of two-dimensional signals like f of, this f is just a name, and we will stick on to the notations of using f and g for functions, or x or y for functions as well, or a or b. It's just some names of the functions. But I hope this will make more sense. F of n1 and n2, where n1 and n2 are the two axes on the space, and f is the value at that coordinate of n1 value and n2 value, for example, depending on the coordinates. So it makes more sense if these are the coordinates, right? Not time, but space coordinates. If these are the coordinates, then this will make it a two-dimensional signal. What is a very typical name for a two-dimensional signal with respect to coordinates? Do we have any name for this? An image, right? An image, a JPEG image, for example, on the screen. 1000 by 1000, 1 million pixels, at coordinates of 100 horizontal and 15 vertical. We have a pixel value. That value here is, for example, the intensity, the gray level intensity of an image. That makes it a two-dimensional image, a two-dimensional signal. That's an example for that, an image. Then can we immediately proceed to, for example, three-dimensional signals? What could be a three-dimensional signal? I'm deliberately using these three terms, n1, n2, and t. For a given time, it makes a two-dimensional signal, which is an image. So it's a changing image in time, for example. It's an example, which means it's a video, right? It's a two-dimensional image changing in time. You may extend the number of free variables to make it 4-dimensional, 5-dimensional, etc., to make them more abstract. But that doesn't change the idea. Now, what changes the idea is whether the free variable are indices, it's an index, which makes them integers necessarily, or a continuous variable. Time in itself is a continuous variable. We have 0.01 milliseconds. But an image, for example, a digital image in this case, it's an indexed function where the free variables are just integers. There is no image. We don't talk about a digital image with coordinates like 7.71, 3.01 pi. There is no such index. The indices are 128 and 64, things like that, right? Just integer numbers. These indices, so this is not valid for indices, will have integer index values like this, and they are called discrete values. These integers are discrete values. A continuous variable like t will have continuous values, any real number that you may think of. And the difference between these two will be notated as a continuous time signal and a discrete time signal. Of course, if we are talking about one-dimensional signals, and from now on, I'm just forgetting about multi-dimensional signals. Okay, let's go back to f of t. If it is f of t, then the time variable, if it is continuous time variable t, then it's a continuous time signal, and the notation will be like this. And if you stick to the notations, that we are using, and if you don't deviate from these notations, then I will be able to understand your answers. If you use confusing notations, I will not understand your answers. This means the time, this t is continuous. For discrete time signals, which have indices as the free variable, will be notated by, again, let's say f, the name doesn't need to change, but the parentheses will be replaced with curly brackets, square brackets. And inside it, we have an index this time, which is usually notated by K, L, M, and N. Like this. So this is discrete time, this is continuous time. The abbreviations are, this is CT, this is DT. Discrete time and continuous time. And their plot representations will also be different. A CT signal could be plotted on a diagram like this. And a discrete time signal must be displayed on the discrete axis of n this time, and the discrete axis of n, this n must only be integers. So how are we going to notate them? How are we going to draw those things? That is this. So what am I trying to draw here? And the indices are -1, 0, 1, 2, 3, 4, 5, 6, 7. And it may go on like this. This is a very typical plot of a discrete time signal. And how am I drawing them? Using a bar, using a line, which terminates with a relatively large point, dot. A full circle. This is a discrete time plot. Right? If you use them in a mixed manner, or if you just confuse these two, then either you're doing something wrong or you're having difficulty in explaining that. So be careful about that. These are simple things, of course. Of course, you plot a continuous time function like this and a discrete time function. Now you understand that you have to draw it like this, but you should be really careful. I have encountered several exam answers when I ask the student, for example, to draw x of t. You see now I'm not saying f, but it's x of t is equal to sine 2 pi t. Now what is this? Of course it's a continuous time signal, and you have to accurately draw it with some legend points. It's a sine wave, sinusoid. What do we know about sinusoids? They are oscillatory signals, and they behave like this. Right? So, within some range, we are going to draw it like this. So, what are these points? What is this point, for example? You have to put proper labels in your plots. When I ask you to plot something, since this is 1 times sine, the maximum is 1 and the minimum is -1. And it starts from the 0 point. What is the period of this thing? That's it. That's among the first things that you have to derive for continuous time or discrete time, but periodic signals. When I say periodic signal, the name already contains this thing, so-called period. So what is the period of this thing? 2 pi. So, and this is, by the way, the axis is t. put 2 pi in this instead of t. It will be sine 4 pi squared. So is it really 2 pi? At this point 2 pi? I don't think so. What is it? It is 1. And this point is, by the way, 0.5. Because at 0.5 it makes sine pi, and sine pi is 0. And sine 2 pi is also 0. Since a sinusoid is periodic as a function with 2 pi, as we have suggested, when the inside argument, which is the angle, let's say theta, when theta becomes 2 pi, it comes back to the starting original period. It becomes the same as the starting point. But what is the t value which makes this angle 2 pi? That is 1, and t is equal to 1. That makes the period to be 1. And the period for continuous time periodic signals will be notated by a capital T. And it is 1. The unit, it depends on which unit you have defined for t, of course. Let's assume seconds, for example. It could be hours, it could be days, or whatever. It depends on your time scale. But seconds is okay. It's just a time unit with respect to your plot. Frequency is usually notated by a lowercase f, and it is the inverse of the period, right? 1 over period. If this thing t is in terms of second, 1 over second has a name. What is the name of 1 over second? Hertz. These are just notations. Now, as I said, I am going to adopt to the notations of Oppenheim's Signals and Systems textbook. Over there, the frequencies normalized in terms of 2 pi, and it has a different name. So the angles are not in degrees, but they are in radians, in other words. If you consider all the angles in terms of radians, then the frequency has a different name. It is this thing. It looks like a W, and I write the W exactly the same way when I write, but actually it means omega in the Greek letter, lowercase omega. And that's why I'm calling this omega instead of W. And that's omega. Omega is 2 pi times f. It's just a scaled version of Hertz. 2 pi times that thing. And therefore it is 2 pi over capital T, similarly. And 2 pi times 1, in other words. So omega is equal to 2 pi. And this is also frequency, and the name is, or the unit is radians per second. When you multiply Hertz by 2 pi, it becomes radians per second. So this is a periodic signal example, and it's in continuous time. Let's continue with continuous time signal examples. In fact, once we have started the concept of periods, it may be a good idea to continue with periodic examples. Let's take a look at this function. It's a function of time, and it is notated in terms of t, so that it's a continuous time function. And let's call it again x of t. The question is, what is the period of x of t, and what is the frequency of it? Sinusoids will play a significant role in throughout this course because they are fundamental signal pieces. Most of the things are composed of summations of several sinusoids. We will notate many of the signals as a combination of sinusoids. Therefore, such sinusoids are important. It's one of the two very fundamental signal forms. One of them is sinusoids. The other one we haven't seen yet. That one is a little bit more complicated. But this is sinusoid. And what is the frequency, what is the period, what's the frequency in terms of hertz, and what's the frequency in terms of radians per second? I guess the easiest answer will be the frequency in terms of radians per second, omega. What is it? This thing, 0.7, is just a shift of the signal, right? It is shifting the sinusoid on the time axis, but it doesn't change the frequency. The oscillation doesn't change. It's just moving to the right or to the left. And a different question now is it moving to the right or to the left? Are we moving it to the right or to the left? That the answer to that, keep it in your mind. We'll come back to that. Okay? But now let's focus to the frequency. What's the frequency of this? Since this is a phase, it's just a shift. This portion makes the variation, and whatever multiplies this t is the radians per second frequency. It's this radians per second. So what is f? Right? It is 10. Why? Because when you multiply 10 with 2 pi, it makes 20 pi. So this is 10 hertz. So what's the period then? 1 over 10. 0.1 second. So this is the period. Now, let's continue with the periods from the continuous time. This is equal to x of t. What is the frequency of x of t? What is the period of x of t? Can you find it? Now, it's a combination of two sinusoids. Now, you have to be careful about what the new period will be. When such a thing you encounter. We know that the period of this one is 1 over 10. Let's call it T1. It's equal to 0.1 seconds. How about this one? This part. It's again another sinusoid. Whether it's cosine or sine or tangent, whatever, it doesn't really change anything. They are all periodic with 2 pi in terms of the angle terms. And the angle is 21 pi t minus pi. This minus pi is just to make things complicated, and it's nothing but a shift again. So we don't really care about that. Forget about it. The time variation is here, and omega here is 21 pi, which makes f to be equal to what? 10.5 hertz. And the period is therefore 1 over 10.5. I don't know what it is. What is 1 over 10.5? You have a calculator, I suppose. If you're not calling someone, can you give me the answer?
0.95.
0.095. and this is 0.1. Now when you combine two periodic signals, one with such a period and the other one with such a period like this, what will be the combined period? Or how will you find? Well, not the multiplication, it doesn't necessarily the multiplication of the two. Think of it like this. Suppose that you have one periodic thing with a period of 2, okay, and another periodic signal with a period 3. When will they meet again as the starting point? They start at the same point, let's assume. What is the next place which combines the two? They will meet at 6, right? Okay, up to 4, it will make another oscillation, and up to 6, it will make another oscillation, and meanwhile, this blue one will make one more oscillation, and they will meet again. So 6 is the combination of the two, which makes everything as the least common multiple of the two periods. Okay. What is the number value which makes a least common multiple of these two periods? 6 is an integer multiple of 2, and it's also an integer multiple of 3. So you must find a number which is an integer multiple of 0.1, and it's also an integer multiple of 0.095. Okay? That's what you need to find. And I guess it will be quite a large number, I suppose. It will be a very large number. The least common multiple will make this t to be a huge number as compared to 0.1. It will be much larger than that. And when you find that least common multiple, the least common multiple will be the period of the combination. And interestingly, since t will be very large, 1 over t will be the frequency of the combination, which will be very small. So the frequency that we may think of as the fundamental frequency I'm talking about, not the frequency of individual terms, but the combined frequency, will not be as high as 20 or 21. It will be a very low, a very small number, probably. Because the least common multiples of 0.1 and 0.095 is a large number, I would say. I'm just inventing the numbers, so I didn't deliberately engineer to make it proper looking or anything. Just arbitrary numbers here. So whenever you encounter such a question, it's usually significant for you to find first the period of the combination of sinusoids. It may be more than two components, of course. Here we have only two sinusoids. There may be another sinusoid or several other things. The combined thing will have a frequency. They will have a period, which is the least common multiple of individual periods, and from there you invert them to find the fundamental frequency. But we are still in continuous time world. Now let's give an example about discrete time. In discrete time, even giving the answer to whether it's periodic or not is an issue. It's a problem. Discrete time is a little bit different. For example, x of n, look at the notation that I'm using, okay? Please stick to that. Don't say x of t or anything. Is equal to sine 100 n. question, part A. Is it periodic? If yes, what is the period? Part B, if yes, what is the period? Now, in discrete time signals, the periodicity must be strict in the sense of the axis. Since this is, for example, n, for example, such a signal standing to the left and to the right, such a signal is a periodic signal. And what's the period? The period is 4. And it is notated with a capital N or something. Not like a capital T. It's an uppercase N. And as the name implies, it must be an integer. So rule number 1, the period of a discrete time signal must be integer. If you cannot find an integer period for an expression, for a discrete time expression, then it means it's not periodic. If the period is, for example, 7.1, then the period is not 7.1 because it's not an integer. But if you find the period to be 7.1, I make a bet that probably the period is not 7.1, but it is 71. Because 7.1 will not repeat itself, there is no index at 7.1, but you go for n such segments, for 10 such segments, proceed 10 times, you will probably reach to 71, which is an integer, and that may be the period. So this is a periodic signal with period 4. What is the period for this if it is periodic? Using the same rule as theta here, what is n that makes this theta angle inside the sinusoid to be 2 pi? When does it become 2 pi? N is equal to then 2 pi over 100. And 2 pi over 100 is not an integer. So you have to multiply it as many times as possible to make this n to be an integer. For example, if it is 7.1 that you come up with, then if you multiply it by 10, it becomes 71, and 71 is an integer, and I will say that, well, the period is not 7.1, but it is 71. For example, if you find 3.5, if you find the period to be 3.5, then what can you say about the real period for the discrete time signal? 7. When you multiply it with 2, when you go 2 times of this thing, it becomes an integer. So this is not the period, but twice of it is the period. So this is what? 2 pi over 100. When you multiply it with what, will it become an integer? When does it become an integer? What is that? 6 months. That multiple must be integer, of course. Right? So twice, for example, or 10 times, 5 times, 100 times, 1 million times. But it cannot be pi times. It must be an integer. When I multiply it with any integer k, will it ever become an integer? No, because pi is not rational. It's irrational, and the decimals are extending to infinity. So no matter how large a number you multiply with, it will never become an integer. Which means it's aperiodic. It's not periodic. Sine 100n. Now I'm sure you have started working with MATLAB in your calculus courses, right? I recommend that you try to plot this thing. Okay? using MATLAB, using the plot tool of MATLAB. Between n is equal to minus 100 to 500. Okay. You might plot it. You will see that it looks like a periodic signal, but that periodic signal looking shape is not precisely repeating itself. It is somehow changing. Within a period, it looks the same as within another period, but they are not exactly the same. Only the envelope shape is like a sinusoid, but the discrete values are not repeating precisely. Therefore, you must say that this one is not periodic. What could be a periodic discrete time sinusoid? It could be something like this. Again, x of n is equal to cosine 200 pi n. Alright? Now we know that inside it is 2 pi times a frequency, a discrete time frequency, times n. And from here, when you pick this f, it makes 100. And the period is therefore the smallest integer, which makes 1 over 100 to become an integer. And what is the smallest k integer here? It's 100. And the period, we can say, for example, is to be 1. Does it really look like a periodic thing with a period 1? Well, of course it is periodic with the period 1. And what is the signal with period 1? What's the discrete signal with the period 1? It's a constant. In fact, if you want to plot this, you have to draw it like this. It is 1, 1, 1, 1, 1, 1. Like this. When n is equal to 0, it is cosine 0. When n is equal to 1, it is cosine 200 pi, which is an integer multiple of 2 pi. So cosine 2 pi is the same as cosine 0, which is 1. So at 1, it is 1. At 2, it is 1. At 3, it is 1. This is a nonsense signal. Right? It's not even periodic, it is constant. A periodic signal with period 1 is a constant signal, flat. How can we make a more periodic looking thing? By lowering the frequency. The frequency of this is too high. So, for example, we can say x of is equal to cosine 0.1 pi n. Okay. This will be a more handsome function. And the frequency here is 0.05, because 0.05 times 2 pi is 0.15. And the frequency is the smallest k times 1 over 0.05, which is 20, right? 1 over 0.05 is 20, and k is naturally 1. You don't need to multiply with anything larger. So when you plot this thing in MATLAB, you will see that using integer indexes of n from minus 100 to 100, for example. Try it like that. It will repeat itself in a period of 20. At 20 samples later, there will be a repetition, an exact repetition. So it's periodic at 20. You must make sure that you have the necessary skills to accurately find out the frequency and the period. That's something critical. Now, so much about periods. Of course, when you combine two discrete time signals, periodic signals like this, you must again find the least common multiple of the periods first, and then evaluate the period accordingly, and then re-evaluate the frequency, and the frequency is 1 over period. Okay? For more than one term like this. It's the same rule. Now, let's come back to this example. This is an example of, for example, if you have x of t, and suppose you plot on the axis, suppose it's finite support, it starts from 0 and it ends at 2. Let's assume so. And the peak is at 1, and this is 1. This is x of t, just an example signal. Plot y of t, which is equal to x of t plus 1. Okay. And one of your friends suggested that it shifts to the right. Yes, you still said that. Now, if you're not very sure about that, I'm never sure about such things. Okay? I never say yes or no or anything. Just substitute some numbers. When t is equal to 0, what is y of 0? So I'm going to plot y of t, and at this point of t is equal to 0, y of t is y of 0. What is y of 0? Y of 0 is x of 1. What is x of 1? This value. And y of 1 is x of 2, which is this value. So obviously it goes on like this. And I'm sure it starts from here. So are you still sure that it is shifted to the right? Of course, it's not shifted to the right. It's shifted to the left, in fact. If the phase or the increment in the variable is positive, it shifts towards left by the amount of that positive value. What could shift it to the right is just the opposite. Another example. Y of t is equal to x of t minus 2, for example. If it is x of t minus 2, I'm sure this new y of t is starting at 2 and extending to 4, shifted to the right. Like this. On the t-axis. Obviously, this minus 2 or plus 1, etc., they don't need to be integers. These are just examples. It could be pi. It could be 9.4. Anything. Just some continuous amounts of shifts. If it is positive, it's shifted towards left. If it is negative, it is shifted towards right. Now, another thing. I'm trying to be quick about this because before ending the class, I want to come to some conclusions. If this is x of t, when I say y of t is equal to x of 2t, now what is that? What am I doing? I'm scaling the independent variable by a scale, 2 this time. It may be 0.1. It may be 1 million, it may be pi. If it is 2, then what sort of a shape do we expect? Will it be a narrower shape or will it be a wider shape? Wider, narrow. Again, substitution. When t is equal to 0, y of 0 is equal to x of 0. So this point is the same. Doesn't change. When t is equal to 0.5, y of 0.5, this is 1, this is 2, this is 0.5. It makes x of 1. And x of 1 is this point. So it increases like this. When t is equal to 1, y of 1 is x of 2. And x of 2 is back to 0. Which means that if I scale the time variable with a larger than 1 magnitude scale, then it will squeeze in time. I'm squeezing the signal. It becomes narrower. The opposite will be wider, of course. X of t over 2, 0.5. From the previous example, you may immediately deduce that it must be wider, and it must be twice wider, of course. So it will be from 0 to 4. And it will be 2, like this. That is the new y of t. Now here comes the critical thing. Is there a hero in this classroom who is able to, without substitution, put it that way, because by substituting necessary values, of course you will find the result, and that's what I would do. But can you immediately tell me what this one looks like? And this is y1, let's say. What this one looks like? And these two are different, as you see. In fact, this is x of 2t minus 2. So do you narrow down first, because 2t means it's a squeezed and narrower signal. Do you first narrow down and then apply the shift? Or do you first apply the shift and then narrow down? They will be different. I have to give it like this. Okay, it's obvious. No problem about that. You have to make sure that you are doing it correctly, and you have to make sure that your instincts are correct. For that, make the substitutions for t. When t is equal, for example, when t is equal to 1, this makes x of 1. Right? When t is equal to 0, this makes x of minus 1, and the x of minus 1 is 0 anyway. When t is equal to 0.5, it makes x of 0. So at 0.5, it starts, it moves to the starting point. So the first one starts from 0.5. And then at 1, it reaches to the maximum. And then at 1.5, it gets down. So the shape is like this. It is not narrow first and then moved by 1. It's different. It is moved, this one moved by 1 first and then narrowed. Like this. The other one, by the way, will be just the opposite, of course. It is first narrowed and then moved by 1, this one. Because the multiplication comes before summation or subtraction. But I'm never sure about such things myself. Okay? I wouldn't jump into a conclusion. Just try to draw these things by yourselves and see whether you can do that. In other words, see whether you can plot this thing for any arbitrary x of t and a and b. X of y is equal to x of a t plus b for any a and b. Right? Is it possible for you to draw these things for arbitrary values or real values of a and b? You'll be surprised that your instincts may be incorrect. But be careful about these things. And it's just the beginning of the representation. We will give many more examples about signals And then we didn't start with the first chapter yet. Okay? We're just messing around with mathematical concepts, whether we are talking actually the same language here. It's the math language, in other words, that we're talking about. And we understand each other. For those who may think of adding or dropping this course, please take a look at the book and please consider the answers that you gave me in the first place. Okay? And we will continue like this the course of